Alright, hey guys, what's going on? So today we are going to be talking about transformations of tensors. We're in the general relativity playlist, and what I intend to do here is lay down the foundation of covectors and then quickly get into the metric tensor so that within the next video or so we actually want to talk about all of the relevant tensors. I want to aim to do this in like one video, okay? So that we can quickly get to the interesting physics. So without further ado, make sure to hit that like and subscribe button, and make sure to go onto my Patreon page if you want to support the channel. And without further ado, let's get into the topic. So today we are talking about transformations of tensors. So we're going to start from the ground up here. Let's start with Cartesian. We're going to take a look at this picture here. We have Cartesian coordinates and spherical coordinates. We can talk about a point in some space as having an x and a y component when we're talking Cartesian, or a theta and an r component if we're talking about spherical coordinates. Okay, we can do this in 3 dimensions as well. In 3 dimensions, this is going to turn into for 3D, we're going to have x, y, and z for our Cartesian coordinates, and for spherical coordinates, we're going to have r, theta, and an extra term to 2 angular terms. So here, I'll write it right here actually. So I'll say for 3D, we have x, y, and z, and then for spherical coordinates, we have r, theta, and phi. Okay. For 4 coordinates, we have ct, or 4 dimensions, x, y, and z. And for 4 coordinates here, we have ct, r, theta, and phi. Okay, so this is 3D. This is 4 dimensions, 3 dimensions, 4 dimensions. Okay, right now we're just taking a look at the 2-dimensional case, just for simplicity. And we can say, well, that if we have an angle here, and this is our radius in Cartesian coordinates, we can describe x, our x-coordinate, as being r cosine theta. Okay. And we can describe our y-coordinate here as being r sine theta. Similarly, in spherical coordinates, we can say r here is, just by using the Pythagorean theorem, x squared plus y squared. That's r squared, so that's why we take the square root. And then our angle is going to be, the tangent of our angle is going to be y over, or opposite over adjacent, right? So y over p, or y over x at point P, right? So to be a little bit more complete, actually, this is at point P, this is at point P also. So all of these guys are going to be at point P. And the idea here is that we can take derivatives. Of these, because x is a function of r and theta, and we can take derivatives of these. R is a function of the old coordinates. So we could say these are the old coordinates, these are the new coordinates. To go from old coordinates to new coordinates, we use some transformation f. So that transformation f is going to take us in the forward direction. We can use a transformation b to take us in the backward direction. And then these are those transformation matrices, right? And the way we work these out is we say, okay, we have some vector, and the vector is described by some distance in the x direction, some distance in the y direction. Well, that's the total derivative in the x direction is going to be dx over dr times dr, right? So that we can get, those guys can cancel essentially, and we get all this cancellation. But we can rewrite this in this way, right here. Right, so the matrix looks like this, and this is our vector in the new coordinates, right? So, or in the spherical coordinates, right? So in one case, on one side of the equation we have Cartesian coordinates, on the other side of the equation we have spherical coordinates, and then this is the transformation between the two. Okay, so this means that in our Cartesian coordinate system and our spherical coordinate system, we have a transformation, and that transformation is given to us by this matrix. Okay? Roughly speaking, we can call this the Jacobian, and we'll talk more about it later. So similarly, we can do this, right? We can say, well, the relationship, if we want the spherical coordinates on this side of the equation, the Cartesian coordinates on this side, this is what the transformation looks like. These two guys are just, this is T inverse, right? Because when we multiply them by each other, we get 1. Okay, and if you know some matrix multiplication, you can find that to be the case. And this is what we get here, right? So x in the spherical case, in the Cartesian case, and this is T inverse 1. And so that is what that looks like. And so we want to keep this in mind. So the idea here is we're transitioning between different coordinate systems. Okay? It's Cartesian and spherical. Let's talk now about covectors, because once we talk about covectors, then everything's going to get pieced together quite nicely. And I want to talk about covectors by considering physics, right? I want to consider a real-life physical situation here. So we want to consider a force. Okay, so force equals mass times acceleration. The acceleration is in meters per second. So if we can measure in meters, but we can also measure in 100 centimeters. Okay, so we go from meters to centimeters. That's meters are much bigger than centimeters, so we're sort of demoting to centimeters. And when we do that, however, we need this 100 factor to come in front, okay? And that's good. So that's going to increase F. So the force increases when we demote from meters to centimeters, okay? So the units decrease, but the force is going to have to compensate by increasing, okay? And that's what we call a contravariant transformation, when you go against that transformation of the basis, okay? If we consider a field, say the electric field equals voltage divided by distance. Well, if distance is measured in meters, and then we measure it in 100 centimeters, well, we're going from meters to centimeters. Again, that's a demotion in the units. We're decreasing the units to centimeters, but the field is also decreasing because we're dividing by 100. Okay, so this is a covariant transformation. It covaries with the transformation of the basis. So the electric field and the force are two fundamentally different types of objects. They transform in two fundamentally different ways. One transforms with the basis, that's covariant, that's the field. The other one transforms against the basis, that's contravariant, that is against the field, right? So when a covector and a vector meet, or when they're applied to one another, this equation, for example, this is something you've seen probably in physics, E equals F over Q, right? Where Q is the charge, Q is a number, F is a vector, and we're going to call E the covector, right? Because these two guys transform different ways. So a vector, and we're going to call this whole thing a covector. We get a number, right? So we can think of a covector as something that maps a vector to a number, okay? So what is a vector coordinate transformation look like? Because here we talked about vector transformations, or contravariant vector transformations. Here we need to now we need to ask the question, what about covector coordinate transformations? So suppose we have a covector in Cartesian space and a covector in spherical space, or spherical coordinates, and we want to know how covectors transform, okay? Because they're different objects than contravariant vectors. So if f our new coordinates in f is equal to this transformation times the old coordinates in f, right? So suppose again, this is in our spherical coordinates, this is in our Cartesian coordinates, and this is that transformation. And f prime times e prime is r. It's a number, right? Because we said when they get multiplied to each other that gives us a number. Then the new components, right? So these guys, this guy is spherical components, spherical. This is going to equal, well, this guy here, that transforms like this. This guy here, well, we don't know how this transforms, so we're going to keep this blank for right now. But we have to say that this is a number, right? Because these have to be a number, right? So whatever's in here has to multiply to this matrix to give us a number. And the way we do that is by reversing the indices, okay? Because then we sum over the indices, and we have new on top here as a subscript, new on the bottom here as a subscript, right? Superscript, subscript, subscript, superscript. When you multiply those two matrices together, you get a number, okay? And so we also want to call this something different because, again, this is a different object than this, right? So we're going to make this subscripted. So covectors, I like to remember below, okay? And so this object has to transform in this way. So f mu is a vector that transforms as this, and that's we're going to call this a covariant or contravariant transformation. E mu is a covector that transforms in this way, and then we're going to call that a covariant transformation. So as an example, dx, so this is a contravariant object, this is a covariant object. So the contravariant object transforms this way, covariant object transforms in this way, and we get this. So you might ask, okay, where's this -1 come from, right? This -1 comes from right here, right? Because these are two of the same things, right? This is describing some distance, this is describing some distance. So it's the same distance, so this has to be just the inverse of this guy, okay? And these are the old components. Okay, so we have now covariant, contravariant objects. We've established transformations between Cartesian spherical coordinates. Now let's take a look at somewhat of an example here. So we talked about, or this isn't really an example, this is just fleshing things out, right? This is our force vector can be written in this way. Remember, it was a contravariant object, so its components increased as the basis decreased, okay? And so this is a contravariant object. We write it in this way. We can also write it in this way here. All right. A covariant vector, it looks like this, and again, this all implies an Einstein sum, which looks like this, okay? And then this here is just so dx, dy, these z's, y's, and x's refer to these 1s, 2s, and 3s. The reason we use 1, 2, and 3 is because it enables us to consider more dimensions, and we're going to want to consider more dimensions later, especially when we start talking about 4 dimensions, the temporal dimension, and so forth. So we might ask now, okay, well, what about, so we said when f is applied to E, right, so a contravariant vector is applied to a covariant vector, we want to get a number. So that means that when we do that, we want to we can write the covariant or the contravariant vector in this way. We can write the covariant vector in this row fashion, so that when we do that, we get a number. This has to be a number, and that number is just the sum of all of this, right? So this times this, this plus this times this plus this times this. We can take out all the numbers, right? So f is just a component, e is just a component, or e1. f2 is just a component, e2 is just a component. So these are all just numbers that get drawn out. This here, however, is weird, right? So these are two basis vectors. And we're going to say that, so we want to multiply them. That's a product, is when you multiply them. This is what we're going to call a Cartesian product. And we're going to define this as as the Kronecker delta. Okay? And so when we do that, all of this can be rewritten in this way. Right? So these are just Kronecker deltas. So we take the Kronecker delta out and we can generalize to mu nu. We can generalize all these guys to mu nu, and we get something that looks like this. And so given the Kronecker delta, it is 0 for everything except for when mu is equal to nu. Then we can reduce the summation to something that looks like this, where we just have 1 mu, right? Because then this gives us f1 e1 plus f2 e2, and we want to go to the maximum number of dimensions we're considering. But that means, right? That means that we can't have something like 1 in e2, right? Because mu and mu these two are the same. They always have to be the same. If this was a nu, then that wouldn't be the case. All right. And so, with all that in mind, we can now talk about the metric. And let's consider if you measure, we can measure the force and the electric field at any point on this curved space. But suppose we're in the vicinity of a black hole. Right? So here's our black hole. Suppose we're in the vicinity of a black hole. All right, I'll call that a black hole. And the value of each vector and covector is going to change as you get closer to the black hole. So here we're talking about this just in flat space. But when things get curved, things have to change a little bit, because this guy here, our metric tensor, and we'll see why one is up and one is down. But the metric tensor has to take into account that curvature, right? Because we can measure the force at this point, but the force here at this point is going to be different, because our basis is going to change, our unit of measurement is going to change, because of, again, time contraction, or time dilation, and length contraction purposes. And so what we get is we're going to need to introduce a basis for this tensor, because the basis can then get applied to these two vectors, right? So this basis gets applied to here, and this basis gets applied here when we multiply the metric by these two vectors. Okay, so this is just a number, this is just a number, it's just a number, so these can get all brought out, and then we get these guys. These reduce down to Kronecker deltas. Okay, this is going to be like a standard calculation you just should probably really get familiar and hang with, because we're going to be doing this type of calculation for a lot, and where we sort of reduce these guys to this, and then these guys are going to drive all of the components to match with the components in F and E here. And so that's going to look like that. And then we get, and so this is all Einstein summed, right? So that means we can flesh this out. And there's more terms here, right? There's more terms because this always has to, this guy always has to equal this guy, right? So this and this are the same. This and that have to be the same. That have to be the same. And then we also have terms like 1, 2. So, and so these guys have to be the same, right? So this has to be a 0. This has to be a 1. And this has to be a 2. All right, so maybe I should, I don't know what I was thinking when I was doing this, but that should be, this should be a 0, this should be a 1, and this should be a 2. So these have to be the same. These guys have to be the same. Those have to be the same. And so another term here would be E1 like that. And then, and so forth. All right. And so it's just, so that's how we measure. So if you measure two vectors, right? So you need the metric to take into account the curvature of space, right? Because again, time contraction, time dilation, length contraction, we need to take that into account, and the metric tensor is going to help us do that. And so the last question here is, okay, so I wrote the metric tensor in this way. How can we get from a metric tensor that looks like this to a metric tensor that looks like this? Well, you just use the metric, right? But you have to use upper indices to the metric such that G, and you can do this for yourself, G alpha mu, G alpha mu equals n, where we live in an n-dimensional space, right? So, and so we use the upper index. We use the upper index here and the lower index to get mixed indices on the metric. So what that means is we can multiply these guys out, right? Bring these two guys out. Here's our Cartesian products. We redefine this guy, because again, this is just a number, to look like G alpha beta. And then here we have these two guys. Okay. There's nothing to change here, right? We can't, because mu's are going to have to change to alphas. Mu's are going to have to change to betas. Since we have no mu's here, we can just get rid of the Kronecker deltas, and we get this. Right? So we go from two lower components, two covariant components, to a mixed metric tensor, one with a contravariant component and the other one with a covariant component to it. All right, so that is the rundown of the metric tensor again, but this time in the context of measuring things on manifolds, okay? And we did a rundown of covectors and transformations as well. And so with all of that being said, we are now going to take a look at the connection. We're going to take a look at the covariant derivative. We're going to take a look at the curvature tensor and so much more in the next video. What I want to do in the next video is give you essentially a rundown on all of the tensors in their intricacies so that we can really get into the meat of general relativity that you're probably not given on YouTube in most places. So with that being said, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel. And I'll see you guys in the next video. Bye.